So, welcome to our Compass Wednesday seminar today on September 8. Our speaker is Jochen Horstmann at the Helmholtz-Zentrum Hereon in Geesthacht in Germany. He has been an adjunct professor here in our OCE department since 2018 or so. And so that was a good reason to ask him to give a presentation for us. I have known Jochen for many years, from the time when I was at the Institute of Oceanography in Hamburg. He was a student there in the 1990s, and he got his diploma degree in oceanography in 1997. And then he went to this place where he still is today, the GKSS Research Center, to do his studies for a doctor degree. And he got his doctor degree from the University of Hamburg in 2002. So he has been working at this Institute for Coastal Research in Geesthacht since 1995, initially in the coupled model systems group, and then he became a scientist there after getting the PhD in 2002 as an employee. And then a few years later, in 2013, he was promoted to be the department head of the radar hydrography group. The place was initially called GKSS Research Center. That was from the 1950s or 60s, when it was founded as a nuclear research institution, and then several years ago they renamed it to Helmholtz-Zentrum Geesthacht, and now just a few months ago they renamed it again to Helmholtz-Zentrum Hereon. So he has been at a few differently named places, but it has always been the same place physically. He has been abroad for a few activities. In 2002. He was a visiting scientist at Johns Hopkins University Applied Physics Laboratory in Maryland. From 2004 to 2005, he was a visiting scientist here in Miami at SeaStars. And from 2008 to 2013, he was at the NATO Undersea Research Center in La Spezia in Italy as a senior remote sensing scientist. He has authored and co-authored more than 70 peer-reviewed papers. That's quite impressive, a lot more than I have. His main research interests are the development of applications for radar and video-based sensors, a particular focus on ocean surface and subsurface processes. In the first years, he focused very much on wind retrievals from SAR images, then on marine radars with the rotating antenna, and that's what he will talk about today. And we are using his radar system sometimes for our own experiments here in Miami in the framework of this collaboration. His group is also involved in HF radar measurements at the German coast. And in the last few years, they have focused a lot on using drones with video cameras. Maybe he will talk about that a little bit today as well. Anyway, the title of his presentation is Marine Radar Wind and Wave Measurements for Short-Term Forecasts. And I think that's all I have to say. So the stage is yours now. Welcome to our seminar.
Yeah, thank you, Roland. Let's bring up my talk here. Yeah, I will be talking about our marine radar, and in particular about the wind and wave measurements in perspective of using these wind and wave measurements from the radar for very short-term forecasts. So if I'm talking about short-term forecasts, we're talking about really only 30 to 60 seconds. And most of this work is actually funded by the Federal Ministry for Economic Affairs and Energy. And this is there's a good reason for this, because there's more and more wind energy coming up in Europe, and in particular also in the German waters. So there's a lot of research being funded in this particular cases in the recent, I would say, 10, 15 years. This work was conducted together with my colleagues working with me, Ruben Carrasco, Jörg Seemann, and Michael Stresser. And I will start with some older stuff we did before so that you get an overview of how these algorithms have been developed in the recent years. Coming back to the offshore wind industry in Germany or also in the European waters, here you see actually the Northern Sea, the southern Northern Sea. And we have a cross between Denmark and England here on the left. That is about a distance of 500 kilometers. So you have an idea of the size of the area. And you see there is a lot of offshore wind farming planned in these regions. And actually in Germany, there is already quite a bit erected here. So in general, in Europe, we have about an offshore wind capacity the end of 2020 of something like 25 gigawatts. And that actually corresponds to roughly 5,400 offshore turbines. And most of them are actually in the North Sea for a good reason, because most of this area is fairly shallow. When I'm talking about shallow, it's typically something like a water depth of 30 meters, which makes it, of course, much easier to install these platforms. So that's one main reason here that we got the funding here, is because they are also interested in winds and waves from different kind of instrumentations. So when I'm talking about our radar, our radar is based actually on an off-the-shelf standard marine radar, which is normally used for navigational purposes. You see it here in the lower left, how it typically looks. It's a fairly cheap system, and it's not heavy and fairly easy to install. And that is actually one of the main reasons why we have focused on this system. At the moment, we have about 12 of these systems operating, and they are really operating all over the world. The standard system you buy off the shelf is here on the left-hand side, and we add to it some specific units. And the main unit is here, this digitizing and pre-processing board with the analog to digital converter, as well as some small software packages which actually pack together the data more or less in real time. What you do not see here is there's a super low noise linear amplifier, which is totally different to the logarithmic amplifier of these systems. We have a step motor. We have had to add this because we do not want to operate the radar in the standard mode, which is a rotating mode. So typically the antenna rotates 360 degrees every 2 seconds, but we wanted to have the capability of pointing the antenna in different directions and keep it there. We have a motor control board to control this engine, and we have a software suite to steer actually the radar. The typical radar we are using has 12 kilowatts, but we have also smaller and bigger systems, but most of our work is based on our 12 kilowatt radar, which we typically operate with a 7.5-foot antenna, but we have antenna sizes of up to 12 feet that gives us a better resolution in azimuth. So as we are rotating, then we get a much higher resolution in azimuth. The best we can get is 0.6, but typically we're working with a 7.5 foot, which results roughly in 1 degree resolution. The system we are using has been coherentized. That means we are actually receiving the coherent signal, and we're actually listening to the signal we're sending out. And that way we are capable of actually measuring, in addition to the intensity, the Doppler speeds. And the typical range resolution is at the moment 7.5 meters. We are working on a system with a higher resolution, but that is a little bit tricky. You can use it on different platforms. As you can see here, there's this coastal system. You see also in my background here, where we do a lot of work with respect to coastal sea state, learning more about coastal sea state. We operate it here on ships, situated up here in the main mast of this vessel. This is the Hereon, And we have one system which is based on this offshore platform in the middle of the wind parks. That's the Pheno 3. Actually, in Germany, we have 3 of these platforms. They are owned by different people, and they allow us to put up our radar there. And we have a lot of additional measurements. And most of the stuff I'm showing tonight will be on these measurements from the Pheno 3. The radar, some processing is done up in the head of the radar. Then the data are transmitted via LAN to the computer. We can do additional data analysis, and the data are stored. And of course, we have access to the radar via LAN or wireless. Typical radar imagery look like here on the left-hand side. You see intensity images, and in this case, the radar is rotating every 2 seconds and generates one image. You see now here the images every 2 seconds, one. On the right-hand side, you see corresponding Doppler images. You see that they are significantly noisier. So this is a little bit the grainy appearance. But you also see the speeds, and can tell you already here that the main speeds you see here in this radar are based on the main wind direction. So you see here the higher speeds when actually the scatterers move towards the radar and when they move away from the radar, because the radar is situated here in the center. You have negative speeds, the waves or the scatterers moving away. We use for the wind speed retrieval mainly the intensity to retrieve proper wind fields. You see here in addition is, as I said, the Pheno 3 platform is situated very close to the offshore wind farms, and actually circled here are the offshore wind turbines. And this park has, I think, 70 turbines within vicinity of our station. We can use this imagery actually to retrieve quite a lot of different parameters. Like I will be talking today about sea state and individual waves as well as winds, but we are also investigating wave breaking and actually wave refraction and all kinds of wave patterns towards the beaches. You can retrieve actually also bathymetry. I believe what it can do best is retrieve surface currents. We get accuracy of about 4 centimeters with the radar of surface currents, even from moving vessels. And last but not least, there's also a kind of surface feature imaging system with which you can see all kinds of manifestations on the sea surface. And the nice thing is here you can see them actually propagating in space and time. So you see some kind of what is going on in space and time with the radar. As I said, I will only talk today about sea state and wind parameters, and I will start with winds. Wind is, for us, was always of interest having wind informations on vessels, because the wind measurements on vessels are often not so good due to blockage or turbulence and wakes induced by the ship itself. But it turned out that for the wind farming, this wind measurements are of big interest, because they have to steer their whole big location of all these individual windmills, because there, as I showed you before, there's a lot of wind farms at the German coast, and the electric grid has only a certain capacity. So each of these wind farms is only permitted to put into the grid a certain amount of power, and they want to get as close as possible to that amount of power. But as soon as they go over it, the wind farm is being switched off. So they try not to go over this limit. And that's what they try to steer. And for that, they need to know a little bit of a short-term prediction. And when we talk to them of what means short-term, they told us like 10, 15 seconds is already fine. If they have 30 seconds, they have plenty of time to accommodate and shift the blades and adjust the wind park to these needs. So that's how we came up with trying to retrieve winds and a particular wind fields from the radar to give some kind of a short-term prediction. When we retrieve winds from marine radars, we have to get rid first of the information of the waves. You saw all these nice wave patterns in the images before. I will come back to these wave patterns, but the easiest way of actually getting rid of these wave patterns is just integrating over time. So you take the mean of a stack of images, let's say like 32 images, take the mean of these 32 images, and then you end up with an image like you see here on the left-hand side. And all these artifacts you see here are mainly due to the wind. On the right-hand side, I plotted now actually the main dependencies. The main dependencies are the wind direction. You see here actually the intensity plotted along one circle here for two different wind speeds over the whole directions. And on the lower plot, you see another dependency, which is the range dependency, as well as the wind speed dependency. So you see here what we plotted here is the wind speed versus versus the intensity, and for different ranges. These are these small lines which correspond to different ranges, distances to the radar itself. So take back message here is the main dependencies for wind speed retrieval are the intensity, the mean intensity, the azimuth, so the wind direction, as well the distance to the radar, the range. We have found a fairly simple empiric function to actually retrieve from the entire radar image a mean wind speed. And in comparison to the data we collected at FLIP, this is an experiment we did many, many years ago, we figured out that we could get a root mean square error of approximately 0.4 meters per second. I must admit this were ideal situations. We did not have rain and we had fairly homogeneous conditions. We had, of course, excellent measurements here, so there was no interference of masts or anything else, and we had very good wind measurements. So we could calibrate the system very nicely, and I would say this is an optimum situation. We repeated these kinds of tests also by calibrating the radar on a vessel with the information available on the vessel. And there we are typically at an error of about 0.8 meters per second. So not as good. The real disadvantage of this whole story is that you have to actually calibrate for every individual setup you're doing, because the marine radars are not calibrated, not radiometrically calibrated. And that's actually what you have to do by comparison to in-situ measurements. Another important parameter, as you saw, is that there's a strong dependence on the wind direction. Of course, I want to get the wind direction from the radar itself. There are many methods you can actually use, physically based. One is actually the 2D dependent or the two-dimension dependency of the wind speed. You have higher backscatter for upwind directions than for crosswind directions. That's how you can look for the upwind peak, as we call it, so for the highest intensity along the azimuth to find the direction. But you can also see these streak-like features you see here in these center images, and you can do some corrections to actually enhance these features like you have here in the lower right. And if you're getting these kinds of images, you can actually use different kind of methodologies to actually detect the orientation of these streaks. And these orientations are aligned with the mean wind direction and turn out to be actually the most accurate way of estimating wind directions from marine radar images. And in that case, you have roughly an accuracy of just under 10 degrees. Here I'm showing you actually our surface feature monitoring system. I told you, you see all kinds of surface manifestation, and we were now moving with a vessel once through this wind park, once we went down and then back up, and you see all kinds of nice features and lee actually of these wind farms. I can zoom out, and then you see actually nicely the impact of these wind farms, of the individual turbines. And actually that I'm just showing you these images to show you that you have information actually also on the wind field. So you cannot only retrieve the mean wind speed and direction in these images, but you can also retrieve a wind speed field. And that is actually the real duty we had in this project, to figure out wind speeds, in particular in front of these wind parks. And actually you also see here which of these turbines were active, because all these which are encircled do not show a wake, there is no wake imaged by the marine radar. So these are actually these wakes you can also see here in this nice image of condensed clouds due to the motion of these farms. And actually we have also, I'm showing you here to the right, an offshore wind blowing over here, some topography, and you do see some kind of gustiness over the water induced by the wind. So the difficulty here is we have to find an empiric function which relates the intensity at different ranges under different directions to the local wind speed. So on the left-hand side, you have these original images I showed you before. You see these wave patterns. And if you take now a mean of 30 minutes, you end up with the image you have here on the right. And now the art is to find a transfer function to relate these intensities to a wind field. And we have found an empiric function. Empirically, this you can do with all kinds of machine learning techniques, but you can also fit some curves. We're using neural networks to solve this problem. And then we have a function which gets from the intensity, the range distance, and the wind direction estimate of the wind speed. In our case, we trained all this with the wind speed at 30-meter height, because that's the lowest wind speed you can get in these wind parks. And as I said, we are also interested in predicting the winds for the wind farms, and they are interested actually at the wind speeds at hub height, which is typically 70 to 80 meters. So we have to even transform the wind speed farther up rather than down, because normally everyone is interested in U10. But for the prediction in a wind farm, we do not have that much time. I told you we have to give them a prediction within 30 seconds. And so the idea here is, how can we predict a wind field from, as I said, we have to remove the waves. So we have to take the mean of a certain amount of a stack of images. So we are taking the mean of 1 minute of images to retrieve a local wind field, and we will do that on the fly. What I'm showing here is actually the wind field retrieved from the marine radar data, and I will compare these to the wind speeds measured at the wind farm itself at a height of 80 and 100 meters. These are the upper anemometers. And I take the mean wind speed from the radar image in these different boxes you see here. They are color coded. You will see then when I start this video that the wind gusts will come in, and you see how it boosts the wind speeds in this first window. And you will see the delay towards the measurement at the pheno itself. I will start this video that you have an idea. So now we're getting more or less every couple of seconds, I think every 10 seconds, we get one image of the wind field. You see here a wind gust coming towards the wind farms. You see how these winds stack up. And actually you see now the wind gust arrived at the station itself. So that's the idea to retrieve on the fly wind fields in the surrounding of the wind farm in a range of up to 3.2 kilometers. So now we came up with a first cut of a radar-based wind forecast system. And keep in mind, this is one of the many tools which will be available for the wind farmers to actually steer the wind farms. I would never ask them to just relate all their changes to our system, but I think it's a nice first cut of the system, and with all the additional measurements they're taking, this could be an effect of steering these wind farms. So what we have here, in the left-hand side, we have the mean wind speed map every minute. This is the mean over 1 minute. And actually, we generate this every 5 seconds. There will be a new image here. We have down here the range time diagram. So you have here actually the time. And far to the right will be the latest wind speed in distance along the main wind speed direction. And then we have up here a forecast for extremes, which works on thresholds. So you actually could look in the future, that this is the time you are in now, and you can look in the future how much higher the wind speed will be, which is coming up. And here's the number of how much higher it will be, 1, 2, or 3 meters per second. And on the right-hand side, you have the wind sensor of the station itself, which we sometimes use to adjust our wind speed algorithm because our radar is sensitive to strong temperature changes. So from time to time, we're adjusting our radar to the main wind speed from the sensor. So if we look into this video, you see now what is happening. You get here always an update. Here the thresholds are depicted. So this is giving you the forecast for a couple of minutes. It's of course getting better and better the closer you get. And this gives you some kind of a estimate of when there is a wind gust coming. I want to note that the scaling and the color scaling is still terrible, but this was a first cut, and our main problem actually was getting the computation times so in a way that you really can use it as a forecast, because there's a lot of number crunching going on to get these results. But we somehow made it. So that's more or less what we can do with winds. Now, if it comes to waves, we have the main advantage of getting waves from the marine radar is you can look in a distance of up to 3 kilometers. And here the idea was, can we actually detect individual waves, propagate them in space and time, and give the sailor or the people in particular in the wind farms, the main problem is when they're getting to the turbines and bringing over personnel, they have to be careful for big waves. And at the moment, they are working on thresholds from the significant wave height measured by a wave buoy in the area. And of course, they want to get bigger windows and be capable of doing more operations at higher sea states, but do not want to risk any lives or get injuries. So the idea here is, can we predict these waves? And can we give them a short-term warning when they shouldn't put personnel to these masts? That's one idea. We had other ideas like also measuring the impact of the waves hitting the wind farms themselves. So it's some kind of a monitoring how much forces have come up to the pile. These things are done with other methods, but we thought maybe also we can do that by monitoring the individual waves with the radar. The classical way of using the radar is retrieving spectral parameters. I'm showing you here the spectral parameter methodology because some of these things we are using also to retrieve individual waves. And the real most important thing we're actually doing is we're converting the radar imagery into the spectral in the wave number frequency domain, and because that's where we can separate the wave energy from the noise of the radar. And that way we get a much better, or I would say, much cleaner wave spectra. And actually, if in that way we can also get only the wave energy, which we can then I will show you shortly that we can therefore also get better and cleaner information from these waves. And the dispersion shell is related to the linear dispersion shell of wave, or the dispersion relation of waves. So more or less, we know where we expect to have the main energy of the waves in the wave number frequency domain. And this is shown in these plots here. You have here the power spectra, so the wave number spectra, and integrated over all frequencies. And if you look at the wave number in the frequency domain, you see here the power. And this is the power which is due to the waves. And this is lying on this so-called dispersion shell, which is defined by the dispersion of waves. And if we just pick this energy and integrate then over the entire frequency, we get actually a much cleaner wave spectra from which we can actually detect much better the main spectral wave parameters, which are listed in this, what we call our radar ocean wave monitoring system. So you can get then the main spectral parameters as peak wave direction, peak wavelengths, peak periods. And the only difficult parameter, which is not so nice to retrieve here, is the significant wave height. And unfortunately, that's, of course, the parameter most people are interested in. And in the past, we had to do a lot of calibration to get somewhat proper significant wave heights. And there we have now used our radar to get this without any additional calibration, but directly from the radar itself. And there, the idea is actually looking, in addition to what so far we have looked only at the power of the radar, the intensity images on the left-hand side. And for this, we are looking now into the Doppler velocities we are measuring with the radar. And in particular, we're looking into the Doppler velocities we're getting actually from up wave direction. So the main peak wave direction we can retrieve directly from the wave spectra to get the significant wave height. We're looking now in the up wave direction. And the main reason is that all these speeds which we see in the Doppler are mainly related to the wind and the currents, but these are constant speeds, and the orbital velocity of the waves themselves. So you see the orbital velocities of waves in here. And when we have some other parameters, which we call like rest, which is wave breaking, shadowing, so when we cannot look behind the wave, and whatever else would lead to some Doppler speeds. So if we look now into these waves and plot more or less time versus range, so we're now looking only in one direction into the waves, and then over time, these images would look, as you can see here, left-hand side intensity, but we're concentrating now on the Doppler on the right-hand side. And you see now that these imagery get much cleaner. And the main reason for that is that we have plenty of pulses to average, because we are now looking, I mean, our radar pulses typically with 2 kilohertz, and each line here, each second you have then something like 200 pulses where you can actually take the mean Dopplers, and then the data get really, really clean. And that's the main reason why we're only looking in one direction. And if we can now take these Dopplers and assume that these Doppler speeds, the variation of these Doppler speeds, are solely due to orbital velocities, and then we can actually retrieve individual waves from these orbital velocities. And what I'm showing here is actually the Doppler velocity. And then if we take these velocities and retrieve, according to linear wave theory, the wave heights, then these would be the resulting waves. And from these resulting waves, we can, of course, retrieve now the significant wave height. And if we do this, we actually get the following results compared to a buoy. That's the nice thing. As I said, that's like a laboratory for us out there at the FINO. We were looking at two storms in this case. So we had significant wave heights between 0 and 5.5 meters. And if we compare these waves from the buoy to the radar, we get a root mean square error of 20 centimeters. Now, what I didn't tell you yet is that the typical results you get from the classical approach, where you retrieve actually the wave height from the signal to noise ratio, where the signal is more or less all the energy which is located on the dispersion shell, then you have an accuracy of typically 0.5 meter. So here you have a way of retrieving actually the significant wave height without any calibration needed and with an error of about 20 centimeters. If you do some calibration, that means you would have to have buoy information. You can reduce the error down to 15 centimeters. But so we believe, like, going over the fully physics approach by considering the orbital velocities measured by the radar to retrieve the significant wave height is a real nice way of doing things and gets you fairly accurate results. Now, these are the spectral informations you get, but we are now interested in actually the individual waves. And we want to predict these individual waves by measuring them actually far away from the radar and then taking the field we're measuring in a certain distance, propagate it towards, in this case, the wind farm, and then maybe be able to give a warning. So now I have to also say this is an ongoing project. We have another year left to solve this problem. We believe we have solved it, but what is still missing is the validation. So coming to how do we solve this? There are two approaches actually you can take. There's a known approach which has been performed before by taking the intensity images, doing this dispersion relation filtering I showed you before, and actually removing the noise and retransferring everything back into the spatial temporal domain. And then you get some kind of a wave field, which you see here on the right-hand side, and you clearly see there seem to be range dependencies, so with distance to the radar, as well as azimuthal dependencies. Azimuthal dependencies are expected with the radar because the radar can actually see the waves only when they're somewhat approaching the radar. So any looking along the wave crests, the radar doesn't image the waves very well. I will come back to that later. So now what we had to develop is how can we get from these surface elevation maps, how can we correct them actually for the range azimuth differences. So we did that again empirically. I hate doing things actually empirically, but it turns out that is most of the time the easiest way. The problem is we prefer doing it physically because then we understand more what's going on. Here we only assume we know the problems, but it would be nicer to really solve them physically. At the moment, we have solved this only empirically. You see here in the surface elevation map corrected for range and azimuth artifacts. And in the next step, we performed another thresholding filter actually telling us what do we believe most? So which of these waves do we actually believe most? All this filtering saw here is not yet fully developed. We believe we should do at some point still a better job, but that's actually where we are at this point. Now that was getting individual waves from the intensity images. Now we can get the same information from Doppler images, but I will come to that shortly. So typically now this will look for intensity images as here. There's a region which is shadowed by the mass, so the radar cannot look well in this shadowed area. as I told you, along the crest, the radar is also poorly imaging waves, so we do not expect to get good results there. So actually, we expect to get the best results in these upper left corners. Getting now the waves from the Doppler information, we can do the same as I said before. We point into the waves, but actually we want a wave field, so we have to now retrieve the individual orbital velocities along the wave direction, but we're only measuring along the direction of sight of the radar. So we have to correct for this geometric effect, which is not a real problem. However, the more we look away from the main wave directions, the less accurate our Doppler measurements are. So we end up with getting more or less also individual waves over a certain range and in space also aside of the main wave direction. And you see here in the upper right, actually areas where we believe we can do a good job. Because if we look too far, we have the shadowing effect. And if we have the shadowing effect, we do not see the orbital velocities behind the waves, and then we cannot retrieve actually the entire wave anymore. So we are limited to areas which are not shadowed. That means that's a disadvantage. In wind farms, that's not a problem, yeah, because you can get the radar very high. But on vessels or so, that is a problem, because typically on a vessel, we have 20 to 30 meter heights where we install the radars, while here on our Pheno project, we have it at 40 meters. And if we would be starting to install it on wind farms, we are always at 70 to 80 meter height. That is ideal for these things. So the end effect, we would end up with an image like you see here. It looks very similar to what you saw with respect to the intensities. There's one big difference. With the intensity images, we have a phase shift of the waves, and we have to correct this phase shift. While with the orbital, getting these over the Doppler speeds, so with the orbital velocities, actually we'll have no phase shift. And that's the nice thing. Now we wanted to combine both methods to get actually a good estimate of these individual waves with the correct phase and hopefully with a good wave height. And again, we have here, we're talking now about this red box here. And now I'm coming to the part where we are propagating this field for a couple of seconds and compare it. And what we did here is we took this box, used this box, put it in a very simple linear model and propagated it over a certain amount of time. And then after 30 seconds, you come from the left-hand side by propagating it with the model to the right-hand box. And what we are doing now, we're comparing this right-hand box to actually the radar measured wave field 30 seconds later. That's what you see here in the lower plot. And if you look at that over time, you do see that we actually get quite accurate individual waves. Now, the only thing we can really show here nicely is that the phases after 30 seconds are still agreeing very well. And actually also the wave heights do agree very well. But what we do not know at this point is, are actually our wave fields correct? And that's more or less the real point we are struggling now with, because how do we validate our measurements? I mean, the simplest way would be taking a wave rider or an AWAC or whatever, but we have problems there, and that's what I will show you shortly. If we look into 60 seconds predictions, you start seeing bigger errors. Still, the phases are quite nice. And don't forget, the real idea here is actually giving a warning system. So the person aboard the vessel doesn't really care if the waves comes 1 or 2 seconds earlier or later. What he really cares about, is there a big wave coming? And if I can tell him 30 seconds in advance or 60 seconds in advance, he can actually tell people, no, we're not going, or stop some maneuvers. So that's the main idea. So even if it doesn't agree perfectly down here in the plot, the information close to reality is already a good information you can give the crew. And the big advantage here is you can get it at any conditions. We do not, the only thing where we are not sure how it will work if it is raining. We know it will be working for most rain situations, but with heavy rain, the radar will fail. So at the point where we are now, we want to do the comparison to wave riders. We have wave riders in the area. Our comparisons turned out to be very, very lousy. And then we were thinking of, because we still believe that we're doing a good job, what is the real problem? And the real problems are, for instance, the internal time delay in these buoys. So the buoy is measuring all kinds of stuff, is computing it, and is transmitting it to our station. At our station, there will be no time delay because the computer receiving the information is the same computer receiving our radar data, so the timestamps are okay there. But we do not know about delays within the buoy's computation. So we are doing an experiment on land now to figure out the time delay inside the buoys. Another problem, which is also significant, is actually the accurate location of the buoy itself, because these buoys are moored with a chain plus a rubber cord. And actually in the area where we are measuring, we have tidal currents. So these buoys are, the currents are moving around on the ellipsoids. And we have typically current speeds there of 0.4, 0.5 meters per second. So actually this rubber cord is stretched a bit together with the orbital motion of the waves and the waves pushing the buoy up and down. The buoy will be snapping back and forth, so changing positions. And yes, everyone would say, why not use a GPS? They have a GPS. This GPS is unfortunately only transmitting every 30 seconds. So for new steps would be putting a proper GPS on board these buoys so we have its positions at all times. And that can only be performed later this year. We expect the buoy to be changed in December, and then we will equip it with this additional equipment. However, we wanted to try to figure out things earlier. So here, what you see here is actually the movement of the buoy with these 30-minute GPS positions for one day. And you see there's a strong movement of the buoy over the day. We're now trying to figure out, is this only true for over the day? Are the neighborhoods close to each other that we can use it? That is ongoing. Then the other idea was, okay, can we actually correlate these things? So to accommodate and try to find the best correlations in time or in space. And here the problem is that we believe we have a time shift. Here you see the correlation over time. And if you look here, then that's a time shift of approximately like 60, 70 seconds, which is a lot because, we need the accuracy under 1 second to do proper work. And you see also here where we correlated in space, you see there's more or less no real good correlation around the buoy, which is this red location. So that's our main problem at the moment in validating our measurements. We have to get some kind of a measurement device in these rough conditions, which actually gives us some kind of a ground truth, and we're preparing to bring out this buoy. Yeah, with that, I hope I am somewhat in time. I summarize what we have done here. We have marine radar wind measurements with an accuracy of roughly 40 centimeters and 8 degrees. We believe we can do some kind of a real-time wind retrieval over a range of 3,200 meters and can predict wind gusts with about 30 to 60 seconds. The retrieval of the spectral wave parameters is old stuff. However, we have improved significantly the calibration, so we can now, without any calibration, actually retrieve proper significant wave heights from the marine radar. That was a very big step. And we believe, unfortunately, can only say we believe we're really retrieving individual waves. We've shown that if these waves are the true waves, then we actually can do quite a nice prediction for 30 to 60 seconds. So as outlook, there's a lot what we still have to validate. And I hope by mid or end of next year, all this has been validated and we have a nice way of measuring individual waves, because that opens up for us as a scientist quite a bit new windows of investigating waves and wave current interactions. Yeah, thank you for listening.
Yeah, thank you very much, Jochen. Now we have 9 people in the audience. That's still a little disappointing. I don't know where they all are today. Anyway, I hope the few who watched it agree with me that it was quite interesting. Questions? Kamal, do you have a question?
I have 2 questions. One is, this is super impressive. I'm a big fan of Jochen anyway. I have one question that only he can answer. Like, what are the kind of disadvantages? We can easily see the advantages, very super impressive. What are some of the disadvantages of the system? And second question would be, I heard that the wind energy or green energy in Germany is not exponentially growing. Rather, there's a stagnation. Is that true? That will be my second question.
To the second one, I only know from our media. There is stagnation. The main reason for stagnation is money. Germany is one of the countries where the energy is most costly at the moment, electricity in particular. And there's the big reason, therefore, is because a lot of money of our energy costs here is going into that industry wing, and people are not really wanting to put in so much more money into it. However, I believe with the ongoing politics and the more and more the acceptance of climate is an issue worldwide, I think that is only a small dip and will go on. Another real problem is actually that our main problem is not the offshore wind farms, because when we were out there, we saw finished offshore wind farms, turbines, wings, everything on there, but no cable to the grid, meaning everything is finished, everything has to be maintained, but they cannot produce energy because the cord is missing. So this is also, I think, more a political problem or some people have not thought it up in the right way. So there was something missing.
Interesting.
So these are some of the problems I know of, but there may be others I'm not aware of. Now the other question, the one I don't want to answer, but I will. Of course, our radar has disadvantages. One thing is where it really doesn't perform well is, and we do not know enough about it. The nice thing is we can figure out when it's doing this, is rain. Rain effects, unfortunately, expand a lot more than others, or at a lot more than the longer frequencies like C-band. So when it's raining, we are getting more and more blind. With the Doppler, we have the possibility of actually detecting rain, meaning no good anymore, which is an advantage too if you do not have the Doppler. But in Germany, it rains a lot. So that's the disadvantage. Another disadvantage is, of course, that at these cross wave directions, you cannot measure much. But for many applications, no one cares because those waves do not come to you. However, keep in mind, we have regions on this planet where we have dual or multimodal seas, meaning you may see the waves from that direction, but not from that direction. And then there comes this problem, where do we actually look to do our retrievals? And fortunately or unfortunately for us, because we want to learn, we do not have these kinds of seas in the North Sea. Fortunately, then our measurements look better, if I'm honest, but we are now running radars at the west coast of France and Spain to learn more about multimodal seas, because there you have swell systems and wind sea systems from different directions. And that is where I'm fairly certain we will have problems, and we want to try to solve them. That are some of the problems we have. And the other then we have also technical problems, because we are only scientists building these radars. So they are not perfect, but that is an issue some engineers can solve.
It looks great. Thank you, Jochen. Very nice to see you. A really great presentation.
I hope I'm live there next time.
Yeah, that's right. We should really invite you in person again. That would be really good. Werner Alpers, do you have a question?
Yes. Yeah, thank you for your nice presentation. It was really excellent to grasp what the issue is. Now, I just have a practical question. So you measure wind gusts, and then the wind, the blades or so are adjusted. Is that correct? Can that?
Yes.
And it can be done really in 30 to 60
seconds. I was also amazed, actually. They can turn the blades, what did they say, 3 degrees in 1 second or so. So these blades can really be changed in their angle very quickly. I mean, 3 degrees meaning in the slope towards the wind. So they can stop these wind farms very, very quickly. This I found amazing, because these things are monsters. I mean, if you pass them with a research vessel, then you see what kind of monsters these are, because the ones out at sea, they have totally different dimensions to the stuff we are used to here at the coast. Our German coasts are actually plastered with these things. Terrible look, but okay. So that was really amazing. They can stop fairly quickly. I do not know how long it takes them really to stop it totally, but even there he said it's works very fast, because they can rotate the blades so quickly.
But they will, I think, react to changes in the wind speed to wind gusts only when it is not so small. So they have to think of the whole grid. They cannot think that we're not talking here about steering an individual turbine. They have to steer the entire grid. Oh. And here the idea was, one radar wouldn't be enough, but you can put several radars, and then you see where the gusts are moving, and then they can react for the whole wind farm. Yeah, the gusts will move through the whole farm. So okay. Now what they're doing, they have their wind vane and trying to retrieve the gust information from these wind vanes. And don't forget, these wind vanes are not in front of the turbine. They're in the back of. There's nothing to measure in front. So it's a big issue. They're also using lidars to measure in the front. So the lidar would always ping through the blades and look. I mean, we know everyone has heard of the lidars looking up, but if they're lidars looking into the front and trying to predict the wind field in front of these wind farms. And that's these people are also working on the same issue, but the nice thing, the lidar can only look in one direction. We have some kind of a surface. Okay. But our main disadvantage is, of course, we're measuring
we are measuring actually the roughness at the surface, and now we have to bring the roughness of the surface we have to bring to a hub height, which is 80 meters. There are a lot of errors we will be making there. So it's only, that's what I try to point out, it's only one piece of the puzzle. And that's exactly what these guys are doing. And unfortunately, all that is secret. They are not telling you how they are doing the entire steering of the grid and what kind of information they're using. And that from that, you will know that every brand or every wind park has its own way of steering this, because it's a big deal of money getting as close as possible to the registered gigawatts to get money.
Just an order of magnitude. How often do they steer? Every day or
no, I mean they don't. The problem they have now is, because it's so expensive, as you shoot over, you're shut down for a while, so you lose a lot of money. So they don't want to get there at all. So they shut down these wind farms much earlier than they have to make certain they will never bring too much power into the grid. I mean, we can imagine what happens if they all power and then the grid starts evaporating. I mean, that's also costly. So that's why this is very well controlled, and they do not get to that. They want to get as close as possible, but as they cannot get there very closely yet because the measurements are missing, they are very interested in these things. I mean, it wasn't even our idea, I must admit. I showed once this video where you see the gustiness in lee of, like here in lee of this island, to one of these wind farmer engineers. And this guy was immediately, as we say in Germany, fire and flame, and asked us if we can parameterize this, because that's what they want. And that's how this project started. So it came more like from the wind farmers rather than us.
Okay.
I find it a little surprising that they can control them within seconds. They can change the adjustment of the blades, and still that's not fast enough to respond to changes in the power. But I guess the whole thing has so much inertia that even if you can adjust it quickly, as soon as it begins to rotate too fast and to make too much power, you need too much time to slow it down again, if that's the moment when you begin to react to it. So you want to react a few seconds before it happens, right? You want to
don't forget
20 seconds before it gets too fast, so you don't need to slow it down. And I thought maybe there could be a brake or something to slow it down, but that would have to be such a large and heavy brake that's probably not feasible. Huh?
Not really. If you have seen one of these axes, I was once on one of these exhibitions. It's massive steel, 2-3 meters diameter.
And if you add a clutch to it
I think they know what they're doing.
Yeah, so then it would go would begin to spin like crazy. So yeah, I see it's an interesting problem. Okay, do we have any further comments from the 5 people in the audience? I don't think so. So thank you again for the nice presentation, which I will upload to YouTube. So I hope it will find a few more viewers on YouTube. Thank you all, the 5 people, 4 remaining people, for coming to the seminar. We will have no seminar this Friday, but next Wednesday at 3 o'clock, Dennis Hansel's former student, Robert Letscher, will talk about some complicated chemical issues. So we will see how many people will be attracted to that. Thank you very much and goodbye.
Yeah, thank you.